Hello, I hope you are keeping safe and feeling excited to start this wonderful semester. Today we are going to focus on the bond polarity. So in other words, we are going to look at how do we determine the bond polarity between any two atoms and how do we represent that. And it takes us to the electronegativity, which refers to how strongly an atom attracts the electrons that are shared to itself. So the most electronegative atom is fluorine, which is at the top right-hand corner of the periodic table. So as you move away from fluorine, the electronegativity decreases, which means that between oxygen and carbon, oxygen is more electronegative. So we can use the symbol here with an arrow pointing towards the atom where the electrons are more likely to reside, and we put a plus sign in the tail to show that the electrons are actually less likely to reside on that atom. So we can either use that sign, the symbol, or we use the delta plus and delta minus. The delta minus, again, here you see, is towards is on the region where the electrons are more likely to reside. And of course, the electrons are negative, and that's why we use that. In general, if the difference in the electronegativity of the two atoms is less than 0.5, that bond is classified as covalent. If the difference is roughly between 0.5 and 1.7, the bond is classified as polar covalent. And if it is greater than 1.7, the bond is classified as ionic. This is more like a general rule. There are some slight deviations, but we're going to try and work with this for the time being. An example we can look at is chloromethane. Carbon has an electronegativity of 2.5, chlorine has 3.0, which means that the bond between carbon and chlorine is polar covalent. So we can show the delta minus on the side of chlorine and the delta plus on the side of carbon. And then we can use a visual representation where we use the heat map. So the red portion is where the electrons are residing more, and this other side is where there are less electrons. We can also employ the concept of intermolecular forces to explain some of the changes in the physical property of molecules. Now let us start with the dipole-dipole interaction. If you look at these two compounds, what do you notice? They're actually the same. There's only a small difference. We have CH2 here we have oxygen. That is the only difference. So the bond between a carbon and a carbon here, the electronegativity difference is 0. So it's purely covalent. The bond between carbon and oxygen is polar covalent. Carbon has electronegativity value of 2.5. Oxygen has electronegativity value of 3.5. So that gives us an absolute difference of 1. So that means oxygen is going to have more electrons residing on it, so then we can use the symbol that we were using before to show that the electrons are residing more on oxygen. So then how does that help us to explain the big difference in the boiling point and the melting point? So isobutylene boils at roughly -7, acetone boils at 56 degrees Celsius. What accounts for that difference? Well, within the intermolecular, within the structure, the intermolecular forces play a role. So the structure of acetone, the molecule is going to arrange itself so that one molecule is attracted to another. So there's this dipole interaction, delta minus, delta plus, delta minus, delta plus. So the dipole-dipole interaction creates a strong effect in the alignment, just like in a magnet, and the molecule feels stable that way. So in order to overcome these forces, extra amount of energy is required to break these bonds for the intermolecular forces first before the molecule can boil. And that is why the boiling point of acetone is much higher than that of isobutylene when the structures are actually alike. Next, let us look at hydrogen bonding. Well, hydrogen bonding is a type of dipole-dipole interaction, actually one of the strongest. And it is formed when fluorine, oxygen, or nitrogen are able to bond to a hydrogen that is attached to another fluorine, oxygen, or nitrogen. So, for example, in water, we can have this oxygen bonding to another hydrogen. So again, we can also have the same thing happening with ammonia, that is the hydrogen bonded to that nitrogen. It can form a hydrogen bond where this nitrogen is attracted to the same hydrogen which is bonded to another nitrogen. So then it forms like a cobweb of network, like a polymerase kind of thing, where the bonds are difficult to break. They are really not covalent bonds. That's why we call them intermolecular forces. But extra amount of energy is required to break those bonds fast. So let us look at this question. Which of the two compounds has a higher boiling point and why? Based on what we have explained, we need to look at the oxygen and the hydrogen. So here the oxygen is bonded to hydrogen, which means in this molecule we are going to have an intermolecular force where the oxygen is going to be bonding to the hydrogen of this other molecule of the same compound. Here we have oxygen bonded to carbon and carbon, so there's no hydrogen bonding. So again, keep in mind, hydrogen bonding only takes place if nitrogen gets attracted to, the nitrogen connected to a hydrogen gets attracted to another one, which is connected to any of those three. So in that case, the boiling point of ethanol is actually 78.4, and then the one for dimethyl ether is minus 23 due to the effect of the hydrogen bonding. Thank you for watching and have a good one.